Good morning, everybody. Last class we have discussed the photoelectric effect. I will just rewind it very fast. This was one of the effect which was not explained classically well. So it was explained with the quantum mechanics by Einstein, and we know photoelectric effect is just when the light beam is incident on a metal plate, the electrons from the metal surface are ejected out of the metal surface, and they get accelerated, and these electrons are called photoelectrons. And we have derived an equation also for this photoelectric effect. The main experimental findings were four findings I have discussed in the last class. This is the connection diagram or the experimental setup for the photoelectric effect to see. And you can see here we have two plates, metal plates. One is positively charged and second is negatively charged using a battery, and we can vary the potential on these plates. And we know when the light beam is incident on the metal plate, electrons from the metal surface will be ejected out of the positive plate, and they get accelerated, and it has a kinetic energy, and they will move or they will be forced to move to the negative plate, and they form a current in the circuit, and we can find the voltage and current in the circuit using the voltmeter and ammeter. So if you increase the voltage given in the positive plate, we can see that these electrons emitted and collected in the negative plate will be decreased. That means the current will get decreased, and at a particular increased voltage to the positive plate, when you increase the voltage to the positive plate at a particular voltage, these electrons will not be emitted anymore, and the current becomes zero. And this was the stopping potential. That means it is the potential, and this is the energy. The stopping potential is the energy required not to emit the electrons from the metal surface, and it should not get any kinetic energy. That means current should be zero. So this stopping potential should be equal to the kinetic energy achieved by the electrons, so that it get cancelled and there is no kinetic energy for the photoelectrons. It will get zero current. So these are the findings, experimental findings in this experiment. First one was there is no time lag between the arrival of light at the metal surface and the emission of photoelectrons. So there is no time lag. It is instantaneous process. Photoelectric effect is instantaneous process. You should remember these four findings, because this will be asked always. So you should remember these two graphs which is shown here, photocurrent versus voltage, and the photocurrent versus voltage for different intensity, and for photocurrent versus voltage for different frequency of the incident light beam. Okay, so first one is there is no time lag between the arrival of light at the metal surface and the emission of photoelectrons. Second one is when the voltage is increased to a certain value, say V0, this is the stopping potential. The photocurrent reduces to zero. That means ammeter shows no reading. So that means the electron is not getting any kinetic energy. All the electrons are in the metal surface itself. It is not emitted and it's not getting any kinetic energy. So that is called the stopping potential. You should remember that. And third one is increasing the intensity of the light beam. There is a light beam incidenting on the positive plate, isn't it? If you increase the intensity of the light beam, the number of the photoelectrons emitted from the metal surface should have the same energy. The number is increasing. The number of emitted electrons is increasing, but the energy of these all electrons emitted is same. So energy will not be changing, but the number of electrons is increasing. So you should remember that. That point is plotted in that graph, which shows the voltage versus photocurrent for different intensity. I is equal to 1I, 2I, 3I. Okay. So if you increase the intensity, the number of photoelectrons are increasing. So photocurrent is increasing. But the energy is not increasing. Kinetic energy of the electron is not increasing. So in order to stop the electrons, we should apply stopping voltage, isn't it? So kinetic energy, this stopping potential should be equal to that kinetic energy. So stopping potential is same for all intensity. See, V0 is same for all intensity because the energy of the electron is not changing. It is same. Okay, so next one, fourth one is increase in frequency of light increases the energy of the electron. So now we are increasing the frequency of the light instead of intensity. Earlier we were increasing the intensity. Now we are increasing the frequency. So see there, when you increase the frequency of the light incidenting on the metal surface, what happens? The ejected electrons from the metal surface has higher energy. So it will have higher kinetic energy. So the stopping potential in order to stop these energies will stop these electrons will be different. Stopping potential will be different for each frequency. So the higher the frequency of the incident beam, the higher the stopping potential we need to stop this. So the energy is increasing there. It is not the number of electrons increasing, but the energy of the ejected electrons is increasing. So here the stopping potential for each frequency nu1, nu2, V1, V2, V3 are stopping potential for frequencies nu1, 2 nu1, 2 nu2. Okay, it's not shown there. The stopping potential for V3, V3 curve is for frequency 3 nu1. Okay, and V2 is for 2 nu, and V1 is for nu. So when you increase the frequency, the stopping potential is increasing, but the photocurrent remains same because what happens there, because the number of electron is same, only the kinetic energy is increasing. When you increase the frequency of the incident light, only the energy of the emitted electron is increasing, but the number of ejected electrons are same. Okay, so these are the next slide. It shows the photoelectric equation, which says that a part the incident photon has energy h nu, and a part of this h nu energy, some energy is used to eject out the electron from the metal surface, and the other part, the remaining part is given to the electron as its kinetic energy. So h nu will be equal to W0 plus half mv square, where W0 is the energy needed to take out the electron from the metal surface, which is called work function, photoelectric work function. So W0 is called photoelectric work function, and half mv square is the maximum kinetic energy. And if you substitute for kinetic energy max as h into nu minus nu 0, if nu is less than nu 0, there will not be any kinetic energy. That means no photoelectric effect, no electrons are ejected. So we should need a minimum frequency to eject the frequency of the incident beam, minimum frequency of the incident beam to eject the photoelectrons. That frequency here it is nu 0, and it should be equal to h, and the energy should be equal to W0, which is equal to h nu 0. And from this h nu 0 we can find out hc by lambda 0, and lambda 0 is hc by W0. Okay, and the stopping potential V0 we can replace it with the kinetic energy max, because in order to stop the in order to stop the electrons which are ejected from the metal surface, we need that much potential, isn't it? That much stopping potential we need to apply in the circuit. So kinetic energy max should be equal to the stopping potential. So we replace it with the EV0, which is energy. Kinetic energy max is equal to V0 is just the voltage. In order to make it in the form of energy, we should multiply it with the charge EV0. Then it will be energy. So EV0 is equal to h nu minus h nu 0. And now we divide whole equation with E. Then we will get V0 is equal to h nu by E minus h nu 0 by E. And here this equation now becomes in the form of y is equal to mx plus c. This is a linear equation, and you can plot y versus x here. Y is V0 and x is here nu. And if you plot V0 on y-axis and nu on x-axis, we will get a straight line, and the slope will be the coefficient of nu there, which is h by e. Okay, m will be the slope. Okay, now we have here what is the consideration here from quantum mechanics in photoelectric effect. In photoelectric effect, we have considered that the incident radiation, the incident light beam contains energy h nu. So it is the packet of energy, isn't it? H nu is only a packet of energy. So here we have considered a light beam as different packet of energy, which is called photons. So each quantum of energy is considered here as each photon, and each photon has energy h nu. So photon has zero rest mass and it travels at the speed of light. This is the consideration, and this explains the instantaneous emission of electrons in photoelectric effect. Okay. Now next we are going to study Compton effect. Compton effect is also one of the experimental experiment which is explained with the quantum mechanics, and it could not explain with the classical mechanics. This is also similar experiment as photoelectric effect, but here the light beam which is here considered here is monochromatic beam of X-ray. Instead of light beam, we take X-rays, and it is scattering with the another material, or here the light beam is incidenting or scattering with, it is having a collision with the another material. It can be metal, or it can be one electron, or any material, and then it is scattered away. Earlier in photoelectric effect, the light beam is getting absorbed in the metal surface, and the electron is getting ejected out from the metal surface, and we are analyzing the electrons there. But here we are having the light beam or X-ray beam scattered with the electron or a material atom, and then the light beam itself we are considering, and the electron also, or the material atom also we are considering. All the here we are considering both the light beam and the scatterer, which is the target, after scattering and before scattering. So we have to consider the energy and momentum of the incident light beam and the scatterer, which is the target, and energy and momentum after scattering of both this scatterer target and the incident beam. Okay, so let us consider an X-ray beam which is incidenting on an electron. Okay, and it says that both the wavelength of primary radiation after scattering, let us consider h nu is incidenting on the electron. The light beam or X-ray beam having radiation wave frequency nu, energy h nu. It is incidenting on an electron, and after scattering it changes its frequency. So it goes with the it goes with the frequency nu dash, having energy E prime. E prime is equal to h nu dash. Earlier the beam has, this is that curved line shows the beam, incident photon, and it has h nu energy, and after scattering with the electron it has now h nu dash. Okay, so incident and a beam and a scattered beam. Now before scattering the electron has energy and momentum, isn't it? So here the electron has, before scattering it is at rest, so it has no energy, it is only the rest mass energy, and it has no momentum. But incident photon has a momentum, P is equal to h nu by c. So incident radiation has a momentum, h nu by c. Okay, and after scattering the incident radiation have a momentum, h nu dash by c, h nu dash by c, and it has component both in the y-axis direction and x-axis direction. So h nu dash by c in the y-axis direction has component which is value h nu dash by c into sine theta. So this light beam going up, having a it makes an angle theta with the horizontal axis. See that, and it will have a